It's just kind of, you gotta like, you kind of figure it out, like, if I.
At some point, you'll figure out how to hold all those together, and then everything's like, oh, wait,
Yeah.
I know that, I know that.
Like, I thought I was kind of lost, so. And then there was like one day where like, I just remembered something at the beginning and like how, like, I don't know, everything, like, it just like snapped, like, and.
Analysis is one of those courses where there are like 6 tricks, and you just have to remember those 6 over and over and over and over. What are we doing? Epsilon over 3 arguments. Oh, crap. Okay. On Wednesday, Tuesday. Tuesday, we were talking about independence and linear independence in the same way that we were talking about vectors having linear independence. And I asked you guys, how do I know if a set of vectors is linearly independent? And we set up the equations, and the only way to have C1, C2, C3 all be 0 was to solve this set of equations. And I said, yeah, but there's a fast way to do that. And somebody said the magic word. Oh, you take a determinant. So I need to know what's the equivalent of this determinant when I'm dealing with functions. So I need to start with a set of functions. So I'm going to call them F1 through Fn. And they're, I've used this term before, but you may not remember it. It's a term about differentiability. Cn minus 1 means these functions are continuous. And each of their first n minus 1 derivatives are also continuous. So the function is continuous, its first derivative, its second derivative, all the way through to the n minus first derivatives. They're all continuous. All the functions and those derivatives, they're all continuous. We're going to make a matrix and take the determinant. The Wronskian of these functions is it's an n by n matrix. In the first row are all of the functions. In the second row are all the derivatives. In the third row are all the second derivatives. And in the last row are all the n minus 1 derivatives. And the bars mean take the determinant. So this is the one crowning achievement of Polish mathematician Joseph Wronski. He wrote an absolutely huge book on vector spaces and linear independence and differential equations. And the only thing that we kept from the book is this. As far as I know, most of the rest of the book read like an acid trip. But I haven't read it, just read discussions of it. Wronski's work was trying to figure out exactly the question we're after. How do I know if a set of functions is independent? And what Wronski was able to show was if we have a bunch of functions and they are solutions to a differential equation. As a matter of fact, to a homogeneous equal to 0 differential equation. Then, on some interval, differential equation solutions always have an interval. Then, the set y1 through yn is linearly independent if and only if the Wronskian is not 0 anywhere in that interval. So the way I tell if a set of functions is independent is to take a determinant, just like we were in linear algebra, and I'm treating my function and its derivatives as the vector in question. Because that vector of functions and derivatives is what we're putting in to our differential equation. It turns out this not being 0 for any x in the interval is an all or nothing deal. It almost always turns out that you're either 0 everywhere or 0 nowhere in that interval. So rather than looking at the general form and then trying to cancel a bunch of crap, it's easy to just plug something in and see if you get 0 or not. An example. Here are 3 functions. I would like to know if these 3 functions are independent or not. I'll go a step further. Let me actually give you the interval. The entire real line. Build me a Wronskian. I'm just going to put the functions in that order across the top row. 1 plus x, x squared. Take some derivatives. What's derivative of 1 plus x? It's a calc class, people. You shouldn't have to stretch for that one. Derivative of x. Derivative of x squared. Derivative of 1. Great, that's twice. Derivative of 2x. Take a determinants. Now here's the sneaky part. You could take the determinant just like this, with all of the x's and everything in there. If I'm going to do that, expansion by cofactors and minors, remember you cross out and do all that, or you could do 3 down and 3 up, because it's a 3 by 3, I can do that. But the bottom row has a bunch of zeros in it. Let's go across the bottom row. Plus, minus, plus, minus, plus 2 times, cross out that row and that column, 1 plus x, x, 1, 1. That's 1 down and 1 up, so I can actually do that one. Equals 2 times 1 plus x minus x, which is just 2. But you also could have actually plugged in an x value, any x value, and then done the determinant. Which, by the way, no matter what x value you put in, you're going to get 2, right? Because this determinant, when I'm finished, doesn't depend on x in the slightest. On the other hand, I could ask the same question here. The problem is I have to write down the derivatives. What is the derivative of e to the x cosine 2x? See, me, this is why we do all these stupid derivative rules in Calc 1, because that's product rule and chain rule. The derivative of e to the x is e to the x. So I take the derivative of e to the x, I leave the cosine 2x alone, then I take the derivative of e to the x, sorry, I leave the e to the x alone, I take the derivative cosine of 2x. What's the derivative cosine? Negative sine. And that'll be minus sine 2x. Oh, chain rule. There's an extra 2. Same thing over here. The derivative of e to the x is e to the x. So I leave the sine alone, and then I leave the e to the x alone. The derivative of sine is cosine, and the chain rule gives me an extra 2. Now I want you to imagine for a moment, we're going to do a Wronskian. I'm going to take f1 times f2 prime. I'm going to take f1 prime times f2, and then I'm going to hope to God that I can simplify this, right? Because to do the Wronskian, I need to do that. That's a 2 down there. Now, I don't know about you, but that sucks. What if we plug in 0 first? If I put a 0 in here, e to the 0 cosine of 0, e to the 0 times sine of 0, e to the 0 times cosine of 0, that's 1. E to the 0 sine of that's 0, so that's 1 plus 0. This is 0, 1, 1, 2. These are independent. because this is either always zero or never zero, 99.999% of the time. We'll come into the one case later. I'll show you exactly when we need to look out for stuff. But if it works at one point, it's going to work on the whole interval. And again, in this case, the interval is R. So what? Why do I care? It's a legitimate question. A set of n linearly independent solutions to some homogeneous differential equation L of y equals 0 on some interval is called a fundamental set of solutions. I'm about to give you the most amazing sentence I have uttered in this class to date. Every linear differential equation has a fundamental set of solutions. This is, in my opinion, the most powerful sentence ever uttered in differential equations. If it's linear, then it's solvable. Period. What's more, every solution will then look like something made up from the fundamental set. Once I know what the members of the fundamental set of solutions are, I know every possible solution is going to look like some linear combination made up of those pieces. I'm going to tell you in advance. The following is the ugliest algebra I've seen all day. I claim these two are solutions to this linear differential equation. This particular linear differential equation has constant coefficients. 1, -2, and 5. They're defined everywhere. These functions are defined everywhere. We already know these functions are independent of each other. We did that earlier. For me to show that these are solutions, means I have to take the first and second derivative, plug it in, and make sure it equals 0, and everything cancels out. But a linear combination would be a general solution. So I could instead just do all the algebra on that. And it turns out every time I want to solve a particular differential equation, the way to go about doing it is to first find those fundamental solutions and then find the values of C1, C2, all the way up to Cn that make it work for my initial conditions. Now, the downside to what I have said so far is I have yet to show you how to find these two functions. Once we have them, I can do a bunch of stuff, but I've yet to show you how to get them. Let me do a simpler one because this is disgusting. I don't like this one. Let me give you a nice. I claim these two, y1 and y2, e to the 2x and e to the 5x, make a fundamental set of solutions for this linear differential equation. Let's find out. First and second derivatives, both of these, please.
X, 2x, 5, e to 5x, 25, e to 5x. Okay, so if I use these, 4e to the 2x minus 7 times 2e to the 2x plus 10 times e to the 2x, well, that's plus 14 and minus 14, that's equal to 0. Perfect. If I use this one, 25 e to the 2x minus 7 times 5 e to the 5, sorry, that's e to the 5x, not e to the 2x, plus 10 e to the 5x, that's 25 minus 35 plus 10, that's equal to 0 also.
are these two functions independent? Because if they're not independent, I don't have a fundamental set. Are they independent? I'm actually going to go ahead and do this the quote hard way. I'm not going to plug anything. Let's just multiply these out. Take this determinant. So I get 5e to the 7x minus 2e to the 7x, which is 3e to the 7x, which is never 0. Because e to the stuff is never 0, and I'm multiplying by a positive number. There you go. These are independent. And that means that the general solution to our equation, y double prime minus 7y prime plus 10y equals 0, looks like c1e to the 2x plus c2e to the 5x. I'm going to call this yc. I promise there's a reason to call it yc later, but for the moment, we'll just call it that. Once I find my homogeneous solutions, fundamental solution set, I've solved every initial value problem that could go with this differential equation. You pick a number for y of x0 and y prime of x0, I'll find C1 and C2. Every time. Questions? Okay. All of this has been predicated on the fact that what I am trying to solve, what my theorem tells me about, is this: a homogeneous differential equation. If I want to solve where the right-hand side isn't 0, well, then I have to do something extra. The first thing I have to do is solve where it is equal to 0. And we call that the corresponding homogeneous equation. Oh, okay, wait a second. That's why we call it YC. It's the solution to the corresponding homogeneous part. Then I add on a particular function related to g of x. Again, finding this one is going to be the extra bit. So we'll call that YP for particular. Every differential equation that is not homogeneous, when we have any particular solution, is found by taking the corresponding homogeneous one, one we got from our fundamental set of solutions, and adding it on. Let me go back to the problem we were just looking at. Y double prime minus 7y prime plus 10y, only this time, instead of being equal to 0, I'm going to set that equal to 24e to the x. Here is a function, 6e to the x. Please notice that if you plug that function in, it works. Because this is e to the x, its derivative, yp prime, is also 6e to the x. So is the second derivative. So if I take those and plug them in here, I get 6e to the x minus 42e to the x plus 60e to the x. 66 minus 42 is exactly 24e to the x. So this thing, 6e to the x, is particular to the 24e to the x thing that was on the equation. But that means that if I want the total general solution to this, it looks like this. Where did that c1e to the 2x, c2e to the 5x come from? Well, that's something that when you plug it in to this equation, you get 0. So stuffing this into the equation adds 0 to your result. And since this piece gave me the 24e to the x, adding this in doesn't change that result. So this is the corresponding homogeneous solution. It's also sometimes called the complementary function. And this is our particular solution. I like thinking of it as C for corresponding rather than complementary, but I didn't want you to run into that phrase and not understand it out of the textbook. There's another example on page 128 that I think is pretty nice. You should look at that one as well. So here's the fun part. Kind of. Given a collection of building blocks for the homogeneous version, that's the basis vectors for our solution space. I then find the one extra bit for my particular solution. I hate to break it to you. This is the exact same procedure you did in linear with free variables and bound variables for homogeneous and non-homogeneous sets of equations. You did exactly this procedure. You ended up with a vector of numbers, and then a vector times S, and a vector times T, and a vector times R, right? Number times a vector, number times a vector, specific to that problem set of numbers. It's the same process. I'm just working in functions instead of vectors. If we had spent a little more time in linear in abstract vector spaces rather than in real vector spaces, we could have examined this as well, because all of the processes we are doing here are exactly parallel to what we did in linear. Except I don't have to do Gauss-Jordan. I'm pretty happy about that. Take derivatives instead. I'm not sure it's a better trade-off some days. Questions? I still have to figure out how to find these. But there's one more thing I should do for the general theory before I do that. Let y p1 of x solve L of y equals g1 of x. Let y p2 of x solve L of y equals g2 of x. We can do as many as you want. I'm just going to stick to 2 for the moment. Then yp1 of x plus yp2 of x solves L of y equals g1 of x plus g2 of x. Particular solutions add, just like vectors add. If you sum the g's, you sum the particular solution. You look at me like I slapped you in the face with a fish. Talk to me.
That's my question.
You sure? That's okay. You add the g's, you add the yp's. You multiply the g's by some numbers. You multiply the yp's by those same numbers. Okay, wait a minute. This is our definition for linear behavior in linear algebra. Particular solutions are linear, just like the whole idea of these differential equations are that they are linear differential equations. So my linear ideas carry through. I can check this. Take the first and second derivatives, plug it in, you'll see this works. I also know that yp2 equals x squared plus 3x solves y double prime minus 6y prime plus 5y equals 5x squared plus 3x minus 16. So notice that the L of y part, the differential equation part, is the same in both of these. Y double prime minus 6y prime plus 5y. It's the same in both of them. If I ask you to solve y double prime minus 6y plus y prime plus 5y equals minus 9e to the 2x plus 5x squared plus 3x minus 16, I know that the particular solution is going to be 3e to the 2x plus x squared plus 3x. I just add the corresponding pieces. If I ask you to solve this instead, rather than running screaming for the hills, I will say to myself, wait a minute, this kind of looks like that. What's the difference between these two? What's the difference between this and this? So I know that the yp will be negative 2 times the yp for this part. And it will be negative 1/9 times the yp for this part. Those same coefficients carry through. The absolute key here is linear behavior. There's another example on page 129, example 11. Jalen? Again, you're looking at this like it hates you. Talk to me. Think about it more and ask me tomorrow because I think that's what you want to do anyway. Talk to me.
Yeah, the bottom.
This one? It was -2 times this thing and -1/9 times this thing. So it's -1/9 times the YP1 and -2 times the YP2. So here's the sneaky part. Where the did all of these things come from? How do I know the e to the 2x and the e to the 5x, or the e to the x cosine 2x and the e to the x sine 2x? Or how do I know where x squared 3 to the x comes from? Oh, sorry, x squared plus 3x or 3 to the 2x comes from? Why those? Well, this whole section has been the general theory of linear equations. Now I want to actually start doing the process of figuring these solutions out. There are several different tricks. Advantage, 99% of those tricks are algebra tricks, not calculus tricks. I don't have to do more partial fractions and crazy integration by parts. I hope will make our lives a lot easier. We'll crack on the derivatives. Won't do as many integrals in this section. But that will be where we pick up tomorrow. So I will see you all then. Have a wonderful rest of your day. Because technically you don't get to ask me questions tomorrow. Tomorrow's not a Q&A day. I got other stuff. No, I think the homework's due following. Because of break. Because the question and answer day is Friday. And then Monday and Tuesday are for break. So it's actually due Wednesday.
We have class.
Oh, yeah.